Good afternoon, everyone. First of all, I want to introduce myself. My name is Yihao Tu, as one of the author in this paper. In this opportunity, I would like to present our paper, which has a title, Security Assist Mechanism for the Industrial Control Systems with Authentication. And here is the outline we will divide into the 5 parts. Let's move to the first part, which is the abstract. Due to the fact that communication protocol in industrial control system don't have identification and authentication, which make ICS less secure. So this study creates 3 identity security mechanisms for industrial control communication protocols. The first one is the central control. The second one is the device to device, also called D2D, and the third one is the hybrid. So by doing these 3 things, you can make sure that people who try get into the industrial network by pretending to be real equipment can do so. So industrial control system and their communication protocol are used in most very industry and critical infrastructure, such as manufacturing, power, transportation, and etc. Recent studies have shown that even though most ICS vendors have recently added security features, there are still serious holes in the authentication system. This has made many researchers worried, so this article will be about ICS authentication to help improve the security of ICS information. And also, this study proposed a way to authenticate industrial control communication protocol, like Modbus, to make them more secure and stop people from joining the industrial network by pretending to be real device, which could lead to information theft or tampering. This study suggests 3 ways that thing might work. So the first one is the central control, which means that all equipment is verified by the central control station and data is sent through it. Our feature is shown in below. So this method avoids double verification, and which is a plus. But it also needs a central control device and will increase latency because the data has to be sent more than once. The second one is the device to device, which is D2D, in which device verify each other trustworthiness by authenticating each other. The pro of this method are that it saves resource and cut down the latency, but the cons are that each device has to be authenticated, and if there are n devices, each device will have to go through n combination of the 2 authentications. And the third thing is the hybrid. Our feature is shown in below. So once the device have proved itself the central control station, the central control station tell other device that the device can be trusted. The benefit of this method is that it avoids double authentication. But downside is that it needs a central control device and it delays slightly longer because the other device have to wait for the central control station to tell to others. So in this chapter, we will talk more detail about our mechanism. So the first one is the central control. At the initialization, embed at the send identification key, also called IDK, cross all device through the certificate authority, also called CA. So the first step is the device A encrypt the IDK using the public key and send it to be the central control station. The second step is the central control decrypt with the private key. And if the decrypt data is the same as the IDK issued by the CA, the device A is authenticated. And And the central control station requires data from the device A to be sent to device to device B. And the central control station update the public and the private key and broadcast the public key and all the device. And next step is the central control station requires device B to encrypt the IDK with the private key and send it to the central control station. The central control decrypt with the private key, and if the decrypt data is sent as the IDK issued by the CA, device B is authenticated. The central control station send the data sent by device A to device B. And during the second one is the device to device. So during the initialization, an identification number IDN is embedded in all devices through the CA. Each IDN in the device is different. After any two IDs are hashed, the send string can be obtained, which will also be stored on all devices. So the first step is the device A requires device to B to communicate with device A. The second step is the device B requires device A to send it IDN send. The third one is the device B hash the IDN of device A and the IDN of device B to obtain a hash value. The last one is if the hash value is equal to the string stored in the device. Device A passes the authentication of device B. The device B requires device A to send data. The hash function is the A one-way function, and it can be simple function such as a plus B mod, but using the simple function will reduce security. And our mechanism of this paper is the hybrid. So the hybrid, the send identification key IDK is embedded in all devices through the CA during initialization. So the first step is the device A encrypt the IDK using the public key and send into the central control station. The next step is the central control decrypt with the private key, and if the decrypt data is equal to the IDK issued by the CA, the central control station tells device B that device A is trusted. So the device B requires device A to send data. And here is the conclusion. So based on the cryptography, this paper proposes three verification methods, which is the central control, D2D, and hybrid, to solve the problem of the lack of the verification mechanism in the original industry control protocol. And it can prove defense capability and ultimately improve the security of industrial control protocols. And that is all of my presentation. Thank you so much.